Okay, I want to keep talking about proofs. So far, we really have two main methods of proving things. We have a direct proof, we have a contraposition and indirect proof. And then we had vacuous, trivial ideas, which really depended on knowing the truth value of one of our pieces. I'm not as fond of that as a generalized method, because you have to know something about the truth value as opposed to looking at the validity of the item. Okay. I want to talk about a different method today. So today, I want to look at something called proof by contradiction. In general formal logic, this is referred to as reduction to the absurd. And the overarching idea is that I want to think about showing something like this. Somebody help me understand this question. If not P arrow F is a true statement, what do I know about P? What's the only way that works? Yeah.
Yes.
Because if it was T arrow F, we'd have a problem. If it's F arrow F, then it's okay. So my overarching statement is if I start with, hey, suppose this thing is false, and then I work through to a statement that in and of itself must be false, my original supposition must be wrong. P itself must be true. Now this sounds like I'm talking in a bunch of circles. I promise this does get a little clearer with a couple of examples. The specialty is to figure out what this false should look like. And our goal is for that to look like two contradictory statements. Because if P and not P, well, that must be false, right? So I come up with something where I see both, hey, this part must be true and its opposite must be true at the same time. We done put something up. My goal is to figure out how I did that and then un-F it. So there are lots of examples of proof by contradiction. My favorite is one of the oldest possible. But in order to do this, I have to define a couple new terms again. So before I actually work out this proof, the proof of this claim, I need to know what these words mean. So, an irrational number, well, ir usually means not. So that means not rational. So my first question is, what's it mean to be rational?
Number would be rational if you can express it as a fraction.
Okay, I need to be a little more precise about that, but yes, if it's a fraction. But one of the things that is almost always said immediately after I say that sentence is, well, I could just write the square root of 2 over 1. Wouldn't that make it a fraction? No. As a fraction, but I want both pieces of that fraction to be integers. I want the bottom to not be 0, because if you divide by 0, your fraction goes. And I want the top and the bottom to have no common factor. Now, the reason for that last part is so that I don't think of 1/2 and 2/4 as different numbers. 2/4 and 1/2 are the same number, but we don't call it 2/4, we call it 1/2 by taking out the common factors. So if I want to claim that this number is irrational, it means I can never, ever write it as a ratio of integers. Now, this particular proof is known to be Greek in its origin. So this particular proof is about 2,300 years old. It's not a new idea, but it was so controversial to the way Greek society, scientists and mathematicians thought that it actually caused several physical fights. People got into arguments that got so heated and so violent with each other, they actually started fighting each other physically. So this actually led to fisticuffs. All right. The way a proof by contradiction works is to start with not the thing we want to show. So my first way to prove this is to say, suppose the square root of 2 is rational. Suppose not. Okay. This is where our proof starts. Suppose not. We just wrote down the definition. I just moved it off the screen. If the square root of 2 is rational, then what does that mean? Our definition of being rational. You can write the number as a fraction. Top and bottom are integers. Bottom one's not 0. No common factors. So there exists A, B, integers, B not 0, A and B have no common factors, so that root 2 is equal to A over B. Ta-da! My number is rational. Crypto. Okay. I need to start playing with these numbers. And my goal is to arrive at 2 sentences that both cannot be true at the same time. Something that must be false. Let's take that equation we just wrote. Square both sides. So far, so good? Multiply across, and I get 2b squared equals a squared. B squared B squared is an integer, right? Because it's integer squared, it's still an integer. That means that a squared is 2 integer. What does that make a squared? A description from Monday. What kind of a number is a squared?
Even.
Even. Hey, wait a minute. I have a memory about squares and odd numbers that we talked about on Monday. We wrote a proof about odd numbers and squares, didn't we? What was that thing we proved on Monday? Ian?
That, in this case, a squared is even than a is even.
That was not what we proved directly. It was the other way around. If a was odd, then a squared was odd, right? That was from Monday. So let me make a note to that. That was what we proved on Monday. We actually wrote a is 2k plus 1 and multiplied it all out, and then showed it was 2 things plus 1, right? But Ian, what's the contrapositive of that sentence? Contrapositive doesn't just mean negate. Contrapositive also means, Seth?
So then we, a squared is odd, or a squared is even implies a is even.
Hey, wait a minute. We have right here a squared is even. With what we proved on Monday, we now know a itself must be even. What's it mean to be even?
Can we divide by 2 and still be it?
And how did we write that on Monday? I was gonna say, you wrote it down, go look. You don't have to recite this from memory. You have notes, you should look at them. I don't expect you to memorize this. You've been doing this for all of 3 weeks. I've been doing this for 32 years. It's been a while, people. Some of these arguments you get used to, some of them are brand new. I get it. What's it mean to be even? Please? Ah! There exists some integer k with a equals 2k. Well, if a is 2k, that means that a squared is 2k all squared, which is equal to. What happens when you square a quantity? Almost 4k squared. I got to square both the pieces. I square the 2 and I square the k. Wait a minute, put that in here. Because that was where a squared was in that previous equation, right? I got a 2 on the left, I got a 4 on the right. Let's cancel that. What does that tell me about b squared? I never said anything about positive anywhere in this entire problem. So this could be negative, it could be positive. Lena? Well, at the moment, it tells me b squared is even, right? B squared is 2 times an integer. So b squared is even. Well, wait a minute. Look at what's at the top of the screen right there. If b squared is even, what does that tell me about b? If b squared is even, then b is even. And now my brain explodes. Why does my brain explode? There is a problem on the screen that is a clear contradiction to something we said earlier that's not on the screen. Why are those two underlined things together a problem? You told me A and B had nothing in common. Now you're telling me they're both even. That means they both have a 2. I can't do that. I can't have both of these sentences be true at the same time. They have a common factor of 2. They have no common factor. So what I just showed is suppose not results in false. And the only way that works is if the suppose not was wrong. Once I run into this contradiction, I back up and I say, oh, the thing I supposed must be false. Which means what must be true? My claim. Which is what I wanted to prove in the first place, wasn't it? Let's take some chewing on for a minute here. I want to show this thing. The best way to approach it is suppose it's false. Work to something that is absurd. These have no common factors. These are both even. My assumption must be wrong. This following of the rules of inference, P arrow Q, P arrow false, only works when P is false, is what is behind all of this. Why was this a big deal to Greek society? Allow me to draw you a picture. Remember that the Greeks tried to think of everything in geometry terms. So, where do I find the square root of 2? I find the square root of 2 by looking at a right triangle. Suppose the horizontal leg of that right triangle is length 1. The vertical leg of that horizontal right triangle is length 1. What is the length of the hypotenuse? Pythagoras, right? I take the square of that, 1 squared and 1 squared is 2, and I take the square root of the results. So Greek mathematicians because they like geometry so much, ask the following question. How do you draw that line? The hypotenuse there. Think about it for a minute. I have to go over and up. That distance is 2, isn't it? I go across by 2, I go up, I go across by 1, up by 1. I went a distance of 2. So what if I went halfway, and then I went halfway up, and then I went over the rest of the way and the rest of the way up? So instead of going in a diagonal line, I went in this sort of zigzag. 1, 2, 3, 4. How far did I go? A half, a half, a half, and a half. That's 4 halves. That's 2. I go over a quarter of the way, up a quarter of the way, over a quarter of the way, up a quarter of the way, over a quarter of the way, up a quarter of the way, over a quarter of the way, up. That's a quarter, a quarter, a quarter, a quarter, a quarter. That's 8 quarters, isn't it? 1, 2, 3, 4, 5, 6, 7, 8. That total distance is, well, me. Now imagine you keep going. You make these steps smaller and smaller and smaller and smaller and smaller. But you keep going over, up, over, up, over, up. The distance will always be 2. But the square root of 2 is clearly smaller than 2. The shortest distance between 2 points is the straight line connecting them. So the square root of 2 must be smaller than 2. How do I get there from here? The Greeks decided, because they were so geometrically oriented, that everything should either be expressible as whole numbers or fractions of whole numbers. And when mathematicians showed that this actually was not expressible as a fraction, people lost their entire worldview that everything we measure should be measurable against each other was broken. And the foundations of geometry, which all of Greek mathematics and most of Greek philosophy was based off of, fell apart. There was an existential crisis in Greece, and people actually fought each other. I know it seems really out there right now, but we're not Greek. Questions? This is a very powerful mathematical tool, the proof by contradiction in general, and we'll use it in a lot of other places. But it's just another method at this point in time. Questions? Roman, earlier you asked me a question about the if and only if statement, right? Let me think about that for a second. I mean, literally, I read this, if and only if, right? Which really makes this, to me, 2 parts. P if Q, so if Q, then P, and P only if Q. So the arrow goes one way, and then it goes the other way. Make sense for the symbol? Which means if I want to prove an if and only if statement, I really have to do 2 proofs. Every if and only if proof is really 2 proofs. And the problem is, I could use any of the methods we've got so far to prove this one. I could use any of the methods we've got so far to prove this one. So if I want to show that these two sentences, these two ideas are equivalent to one another, that one implies the second implies the first, I really have to do both proofs. These are often called equivalent proofs, equivalence proofs. Or another way to say it is that the statement P and Q are equivalent statements. Now, it turns out if we can do it for two, we can do it for more statements. So quite frequently, we'll get a list of things. It'll be like, all of these are equivalent to one another. If you know any one of them, you know them all. But because each piece of this is a proof in the style we've already done, it's just a matter of recognizing that whenever you see something about statements being equivalent, you really have to do more than one proof. Questions? One of the homework problems I gave back to you in this set asked you to find counterexamples, right? Well, counterexamples turn out to be a very important piece involving in proofs. Because a lot of our claims, a lot of our statements are universal statements. If a squared is even, then a is even applies to any square number, right? If a is odd, then a squared is odd, applied to any odd number. As a matter of fact, any sort of statement of the form for all x p of x, what's the opposite of it? What's the negation of this sentence? What?
There's just an X or not.
Right. So if you want to show that a statement is false, a claim is false, all you have to do is find one where it's broken. Finding that one could be a major pain in the ass, but all you have to do is find one. Again, I need the definition of a term. We'll define this a little more precisely in chapter 4. I need to start with what does it mean for a number to be prime? Ian?
The only portions of that number are itself.
Aha. Right. You can't divide by anything other than the whole thing or one. So if you take a quotient, a ratio, you either get the whole thing or you get one because you divide it by itself. The only factors, the other way to phrase that, an integer that has two positive factors, one in itself. Quite often we use the word distinct in there. That means that one is not prime because the only factor of one is one. There's not another factor. Here's a claim. This one is false. This is an example of bad recursion. Well, obviously, all odd integers greater than 2 are prime. 3, only thing that divides 3 is 1 and 3. 5 is prime. 7 is prime, and so on. Must work, right? What's the next number? I actually saw this written up as an example of why you can't just start listing things and say, oh, well, clearly from here on out it's going to work. Let me give you a bigger one. Take a number, square it, subtract the original value, add 41. The answer is a prime number. Grab your calculators, people. Put in 1. 1 squared is 1. 1 minus 1 is 0. Add 41. You get 41, right? Put in 1, you get 41. 41 is prime. What happens when you put in 2? What do you get when you put in 2? 43 is also prime. Nothing divides 43 except 1 and 43. Put in 3. Nine minus 3 is 6. 6 plus 41 is 47, which is also prime. Put in 4. 16 minus 4 is 12. 12 plus 41 is 53. 53 is prime. I'll be here for a while. Every number from 1 to 40 works. All of them. Put in 41. Notice the problem? You're subtracting 41 and then adding 41. You end up with 41 squared. That's divisible by 41, not just 1 in itself. But I didn't know until I started checking. Hey, there's a counterexample, but it's way out there at 41, not right at the beginning like 9 was in our other example. Finding the number that is the counterexample. You could be here a while. It is sometimes, but not always, difficult to find out where you've made a mistake in writing an argument. I have here a guaranteed mistake. I hope all of you will agree with me that that is false. Last time I checked, 1 was not equal to 2. Sure about that? Find the mistake. I multiplied by A on both sides. Then I subtracted B squared on both sides. Okay. On the left-hand side, I have A squared minus B squared. Back to algebra class, that factors, right? The difference of two squares. What's the factoring on that side? And over on this side, there's a B in both parts, right? So I'll pull out that B and I'll leave A minus B. Oh, wait a minute, I've got an A minus B on both sides. What can I do? I can cancel. What's the very first line say? Well, that makes this side B plus B. So 2B is the same as B. Cancel the B's, I get 2 equals 1. If you believe every step I made, then 2 is equal to 1. I will loan you $1 today. You have to pay me back 2 right now. Clearly, I'm lying somewhere. Where's the mistake? There's got to be a mistake. Because if there isn't a mistake, the entire rules of arithmetic fall apart. Here, unfortunately, no. I can subtract as long as I do it on both sides.
Where you pull out the B underneath the B squared?
So from here to here?
Yeah.
Well, this is A times B. That's the distributive rule. That's B times B. So that's still fine. I just used the distributive property to pull that back. Seth?
Canceling the A minus B in parentheses.
Why?
The 0.
Canceling. Emily has said it without even thinking about it. Canceling is really dividing. What's the one thing you're not allowed to divide by? And A minus B is 0. It's hiding. We don't think of division and canceling in the same breath, but they really are the same thing. And so here is another case where what we want to say and what we actually said are different. This is one of the reasons that a lot of people get really pissy with proofs. Because it's the finest little detail where it's like, well, of course I can cancel. Can't I? But this is the same idea as misplacing a semicolon and hunting for it. And all of that lovely code you have to work your way through, right? Where's that stupid syntax error? I'll find it eventually. It says the syntax error is on line 162. Line 162 is blank. Where the hell is it? It's like 8,000 lines earlier. Sometimes it isn't a mistake in our logic. It's a mistake in our assumptions. It's a way we write the statement up. We just used this one. I know this is true. If n squared is even, then n is even. We know that's a true sentence. But I'm about to write a bad proof. But before I do, you have a question?
So you said A minus B equals 0. Where do you get that from?
A equals B.
Okay.
If A equals B, if these two numbers are equal, I subtract them, what do I get?
Okay, I just wanted to make sure I got
Yep.
this.
I know this sentence is true. But how do I write a bad proof here? And again, I'm not making this proof up. Somebody else already turned this in, and I had to go, wait a minute, why is this wrong? Well, that makes sense. That's the entire proof. And it's wrong. But help me understand why it's wrong. What? Even if I wrote that L was an integer, I'll actually go ahead and write that in here. L in the integers. Ian. There's nothing up here about L. There's nothing up here about N. It's all about N squared. And then out of left field, you go, okay, well, that'll be even. There's no following, there's no connection there. It gave me my answer because I defined my answer, right? Said, yes, N is even by fiat. Poof, here you go. That's what that first sentence says. Now let N equal 2L. Okay, then you told me N is even. But where'd you get that from? It came to me in a dream. Doesn't cut it here. This is a non sequitur. It doesn't follow. Literally out of sequence. This second sentence doesn't follow from the first one. Something we will see often is this exact sort of idea where you claim something to be true without necessarily having written through the supporting idea. Questions? Just as I said earlier that there were a huge list of fallacies available in oratory and rhetoric, and in logic, we really only cared about two of them, the inverse error and the converse error. There are dozens of mistakes in proofs. Finding them and figuring out what is the gap in the reasoning is a non-trivial problem. A short diversion. We used Pythagoras earlier, right? Pythagoras says that if you've got a triangle, you have a squared plus b squared, you get c squared, right? And all of those numbers are integers. Well, in the mid-1700s, a guy by the name of Pierre de Fermat, said, you know, if you change that power, you can't do it. If you make that a third power, it's never going to work. A fourth power, it's never going to work, where all of the numbers are integers. And interestingly enough, he did this in a book of number theory, Arithmetica, by some Greek geek, whose name I've forgotten at the moment. Diophantus, knew it would come back to me. He wrote this in the margin of one of Diophantus's books. And underneath it, he wrote, I have a lovely proof of this fact, but the margin is too small to write it down. Nowhere else in his notes ever did we find a written proof of that result. This was known because we found results or wrote proofs for all of his other theorems. This became known as Fermat's last theorem because it was the last one we hadn't proved. And over the course of 250 years, people were like, well, let me try this, let me try this, let me try this. And they wrote dozens of different papers and dozens of different starts. And all of them had at least one mistake in them. All of them. Until a guy by the name of Andrew Wiles. I believe in the year 2003, wrote a proof on rational points of elliptic modular curves. I know what all of those words mean. I have no idea what the hell they mean when you put them together like that. And he gave a series of 3 talks at a conference. And at the very end of the conference, the very last talk, he wrote, and this proves Fermat's last theorem. He'd been working on this for 7 or 8 years at that point, without telling you. And people are like, wait a minute, he did it? And they started to read through his proof and to take it apart and to make sure everything followed. And in the middle, he made a reference to something called the Taniyama-Shimura conjecture. And a couple of people went, I don't buy that. I think you missed something here. It took him 2 more years to plug the hole. Because this proof and this problem had been unsolved for 250 years, people had started to offer things like prizes. Andrew Wiles was awarded all of them at the end of 5 more years of discussion as to whether or not he plugged the hole correctly. I think the smallest one was $300,000. Nice work if you can get it, right? The problem had been open and unsolved for over 250 years. By the way, there's a great episode of Nova on PBS about this, about Wiles' proof. There are several books. If you're at all interested in this sort of idea, take a look at the Google, the Wikipedia article on this is not bad and has links to both of those, the video and the book. There are lots of other ways to do proofs, but they all fall back on those 3 primary methods: direct, indirect, and confidential. It's how we mix and match, and we'll start doing some of that mixing and matching on Friday. Note, we just finished 1.7 today, which means it's due 2 class periods from now. You just gave me 1.6, right? What does that mean is due on Friday? I will see you all on Friday. Have a wonderful day. If you came in late and still have homework for me, come bring it up and I'll give you the one I was giving back.